In Learning Target 34, we're going to be looking at conservation of energy again, but this time in systems where there's multiple connected objects. So they give the example of an Atwood machine where we have two masses that are moving and they're connected by that string. So what we really need to do here is just go back to our definition of conservation of energy, or our idea of conservation of energy, which says that for any closed system, the total energy at the beginning of the problem is going to be equal to the total energy at any point in the future in that situation. Now, the closed system idea just means that we're going to be looking at certain objects the whole time, and we'll consider what each of them are doing at the beginning and at the end, and that that closed system isn't impacted by outside objects. That we don't have a meteor coming in and screwing things up halfway through the problem. That would make it more difficult to calculate. We'd have to include the meteor at the beginning and at the end of the problem. So they give the example of the Atwood machine. Let's do one a little bit different. Let's look at a trebuchet. Now I know you're thinking, hey, Mr. Bennett, that looks an awful lot like a catapult. Well, as I understand it, the difference between a trebuchet and a catapult is just in what they use to propel that object. So this machine has a big heavy weight on one end of this lever, and it's going to use gravity to pull that down and launch the rock. Now, if it were using some kind of a tension or torsion force at the bottom, that's what makes it a catapult. This one has the weight going down, so that's a trebuchet. Or maybe I'm totally wrong, but regardless, we're going to use this thing to launch a rock at guys we don't like, I guess. So we're going to be having a transfer of energy here from this 1,000 kilogram mass and its relationship with the Earth, which is beneath it, so our Earth needs to be part of the system. That gives that system, just the mass Earth system, or the 1,000 kilogram mass and the Earth, that gives that potential energy, gravitational potential energy. As that falls down, there's going to be less and less potential energy due to gravity, and then this rock is going to move upward, and it's going to gain some of that potential energy from gravity. It's also going to be moving, so it's going to be gaining kinetic energy as well. So in these problems, I like to just start with total energy at the beginning is equal to total energy at the end, or at any point in time, just to remind myself of how I'm setting up this whole problem. My next step that I like to do is just identify what types of energy are present in the initial state and in the final state. So initially we've got potential energy from gravity, and that's initial, so I'll make it a not, UGO I guess, but mu or UG not. And that's coming from this mass, the 1,000 kilogram mass. And there's no motion there, there's no kinetic energy, there's no springs or anything stretched or compressed here, so no elastic potential energy. So that's it for the initial side. On the final side, we've got this rock now that's up high. This one is down as low as it can get, so we'd say it's at a minimum value for potential energy. Might as well call it 0 at that point. This one's got some potential energy, and it's also going to be moving, so we've got some kinetic energy there. So now I can substitute an equation for potential energy, and again for potential energy, but this time at the end. And for kinetic energy, we'll do 1/2 mv squared. Ultimately in this problem we're trying to figure out what velocity this thing is moving at, or what speed it's moving at the very end of the problem. Oops. Back into that. So we're going to need to know how much potential energy it has at the beginning and at the end. We use that to figure out how much kinetic energy it has at the end, and then we can take that and put it into the equation and figure out how much velocity it would have to have that much kinetic energy. So initially we had that mass of 1,000 kilograms. It was up high. So I've got two m's here. I don't have those labeled very well. Maybe I'll just do a 1 and a 2 for these, just so we can distinguish those. Make this M1 and this one M2. Always good to clearly so we don't get things confused. So that mass was 1,000 kilograms times the free fall acceleration for gravity, 9.8 meters per second squared, times the initial height, which was 3.5 meters. That's going to be equal to, let's see, the mass here, we're talking about the 100 kilogram one, times 9.8 meters per second squared, times the height of that rock, which is 6.5 meters, plus 1/2 times the mass, again, 100 kilograms, times the velocity squared. So now we see we have an equation with just one unknown, and so we can solve for that. So over here, the 1,000 times 9.8 times 3.5, that'll give me a number of 34,300 joules. The 100 times 9.8 times 6.5, that'll give me a number of 6,370 joules. Plus 1/2 times 100 is 50 kilograms times v squared. If I subtract the 6,370 from both sides, I get 29,930 joules is equal to 50 kilograms times v squared. Then I'll divide both sides by the 50 and square root both sides. And on this one, I'm going to get an answer of my speed is equal to 23.6 meters per second. Definitely not something I want flung at my house.